All right, guys, welcome to our lecture on bonding. Hopefully you guys remember from last year, ionic, covalent, that type of thing. And you can see the corresponding information be in chapter 8. So even if I'm not assigning anything from chapter 8, if you want to supplement your understanding of the material, that's the chapter you'd look at. I think you want one of the regular tellers, not the fortune tellers, you want the bank teller. Chemical bonds, three main types, guys. Ionic bonds. Remember, electrostatic attraction between ions, metals, and nonmetals. Remember, metals tend to lose electrons, nonmetals tend to gain, requiring a positive negative charge. What holds them together is electrostatic attraction. That's an ionic bond. Covalent bonds, you guys remember, exist between nonmetals. And what happens is with nonmetals, remember, both of them have a high electronegativity. That means a strong attraction for electrons. So when they come in contact with each other, neither is going to pull electrons from the other. So what are they going to do to achieve a noble gas electron configuration, the stability associated with that? They're going to share electrons. And then we have bonds which holds metal atoms together, which we call metallic bonds. Okay, ionic bonding first, metal, nonmetal. So you guys can see, remember there's an ionization energy, and sodium has an ionization of 495. That means it takes 495 kilojoules energy to remove electrons from 1 mole of sodium atoms. You guys will look, when we talk about electronegativity or electron affinity, notice for the nonmetals on the right side of the periodic table, notice they have negative values. Remember, that's the tendency to attract electrons. When a chlorine atom attracts an electron, it tends to give off energy, and therefore that would be indicated with a negative enthalpy. Okay, so now we're talking about, so now we have the, we're talking about a metal and nonmetal interaction, and what this is saying is there's going to be an electrostatic attraction between those oppositely charged ions. Okay, so you guys, a new term for you, it's called the lattice energy. Once again, sorry guys, here's what like an ionic compound would look like. Like for example, this would be a salt crystal. A little piece of salt would have alternating sodium and chlorine atoms. This would be a lattice structure. You can see it alternating. This would be the sodium plus ions, and these would be the negative ions. You guys see the positive ions are surrounded by negative ions, and the negative ions are surrounded by positive ions. And so lattice energy is described as the energy necessary to fully separate all of those ions from each other. So obviously, the higher the lattice energy, the more strongly those ions are attracted to each other. We can use this this formula. It might look a little difficult, but it's really no different than what I think I've shown you guys with magnets, right? You think about, you have magnets. We have a North Pole, South Pole have an attraction for each other, much like oppositely charged particles, right? What's going to affect the charge, the force of attraction? What's going to affect the force of attraction between them? Won't the distance? You guys see there's a distance factor. You can look at this as like the energy holding together, or the energy holding together. You can see the larger the distance, when you agree there's going to be less of a force of attraction, less it's going to have a lower lattice energy. And then there's, you guys know, whenever you have a K in an equation, that's just a constant to make the equation true, so don't worry so much about that. Q1 and Q2, that would be the size of, you might say the size of the magnets, right? You guys can imagine a lot stronger attraction if we have a larger magnet or a larger charged ion. So it's the distance between the ions and the size of the charge of the ions. And you can see that's in the numerator. The larger that the charge, you can see the larger in the numerator is going to make overall the lattice energy larger. So I don't know if you guys can see this, but look, we've got lithium fluoride, lithium chloride, lithium iodide. You can see the lattice energy for these. So if you guys look on a periodic table, so you can see the metal, for example, if we're going to compare, the metal is the same. What's different is the nonmetal. So when lithium is combined with fluorine, it has a lattice energy of 1030. That indicates, the high lattice energy indicates that those ions are held together very strongly. So why would those be held together more strongly than the chlorine or with the lithium with the iodine? What you guys should know is you go down in the periodic table, the atoms tend to get larger. So if you think about it, if the ions are larger, wouldn't you guys agree, larger ions are going to be kind of further from each other as opposed to compact, smaller atoms that can come closer together. So what the larger atoms indicates a greater distance between the protons and electrons of each of the adjacent atoms, and therefore less of a force of attraction, and therefore a lower lattice energy. So that would explain why they're going down as the atoms get bigger. Now you look at some of these values. Now all of a sudden, look, these are like no larger than 1,000 kilojoules per mole. But now look at this, MgCl2, strontium chloride, magnesium chloride. Now we're in like the 2000s. What can explain why these ones, for example, have so much stronger lattice energy than these ones? Well, if you look, all of these, they're alkali metals, +1 ions, with halogens, -1 ions. Now look at this, magnesium and strontium, if you guys look in your periodic table, those are the alkaline earth metals. Those acquire a +2 charge, and the chlorine would be a -1. So really, what's the biggest difference? Now all of a sudden we have a greater charge on the ion. You guys remember, we liken that to, this is kind of like this. These hold together, right? You can see there is an attraction between them, not very strong. But then, if we have ions that have a greater charge, it would be like this. Much stronger attraction due to the increase in the charge on the ion. All right. So what do we find that affects the lattice energy? It increases with the charge on the ions, we noticed that, and then also it also increases with decreasing size of ions. Just think about it, guys. Smaller ions can get closer together. Just think about magnets get closer together, the force of attraction is going to be greater. The greater the energy holding those, the greater the amount of energy necessary to separate those. Okay. This is just saying, right, you remember metals are going to tend to lose which electrons? Just their valence electrons, right? And that explains why sodium's first ionization energy is relatively small, but then its second ionization energy is like 10 times. It's kind of like looking at the sodium, alkali metal has 1 valence electron. That one's relatively easy to remove because that's in the third energy level or the third shell. But then if you're going to remove the next successive electron, where's that found? That's found in the second shell, much closer to the nucleus, a lot more difficult to remove. Okay, covalent. You guys remember, this is when atoms share electrons, and that's going to be between two nonmetals. And so this is showing like two nonmetals, and the electron, the valence electron, in this case would be shared between the two nuclei, and that's what's holding together as the two nuclei have an attraction for the valence electrons of both. So there's several things that are going to affect the strength of the covalent bond. There's an attraction between the electrons and the nucleus. There's repulsion between the electrons, and there's also repulsion between the two nuclei, right? You guys remember, like charges repel, opposite charges attract. You guys remember we were talking about last year, you can have atoms can share electrons, but you have to then look, are those electrons, those valence electrons being shared evenly or unevenly between the two nuclei? Look at here, this is F2, so two fluorine atoms. You can imagine they're going to attract valence electrons, because by doing that, or share valence electrons, they can achieve a noble gas configuration. Well, you would imagine both fluorine atoms have the same electronegativity, so wouldn't you guys agree if they're going to share a pair of electrons, won't those electrons be shared evenly between those? We'd say that's a non-polar, polar means sides. That's a non-polar covalent bond. But now look at this bond. We would expect a bond between hydrogen and fluorine to be covalent. Why? Once again, the easiest way to think is, oh, they're both nonmetals. If they're both nonmetals, they both have relatively high electronegativities. They both have an attraction for electrons. So you're going to expect them to share electrons, but the question is, will they share them evenly or unevenly? Well, you would then compare the electronegativities, and you could either look at electronegativity chart, or you would just know, guys, remember, where are the most electronegative atoms? The upper right. Fluorine is the most electronegative atom, so you would expect that to have a stronger attraction for the electrons being shared between hydrogen and fluorine, and therefore the shared pair of electrons are going to spend more time around the fluorine nucleus, and therefore it's going to make this side of the molecule partially negative, whereas this side that is less electron dense will be partially positive. Fluorine pulls harder on the electrons it shares with hydrogen than hydrogen does. Therefore, the fluorine end of the molecule has more electron density than the hydrogen end. You know what, for sake of time, I think I'm going to skip this. It says, I got the job. I start Monday. Wake up. What? You're having a nightmare. Actually, that's a good word. Hopefully you guys don't have that kind of mentality, because that's the mentality losers have. You guys should be looking forward to a good paying job, a job that's going to stimulate you, and that comes from getting a good education, right? So you guys can pick the job that you want rather than just do the job, the only one that they'll hire you. Electronegativity, we talked about this. Electronegativity is the ability of atoms in a molecule to attract electrons to themselves. And this is just showing you here, for example, fluorine, upper right, has the highest electronegativity. And then you'll notice the metals have a much lower, they're showing you by the size of the I guess, the square. Metals have a very low electronegativity. So, what this is saying is you go on the periodic table, we did this last lesson, I believe. As you go right on the periodic table, electronegativity increases. As you go down, electronegativity decreases. Therefore, upper right, with the exception of the noble gases, should have the highest electronegativity. So when two atoms share electrons unequally, a bond, we call it a dipole. You can see pole means end, like you have the North Pole and the South Pole of the Earth, right? Those are ends of a weak magnet. The Earth is a gigantic weak magnet. So that's what pole means. So if something's polar, it means it has ends. Di, you guys should know, means two. So just like if electrons are spending more time on this side, it's going to make this side of the bond or molecule more negative, and the side that they spend less time on is going to be positive. That's what we mean when we say it has a dipole. So you guys will look, there's several compounds, HF, HCl, HBr, HI. You'll see there's a bond length. You'll notice the bond length gets bigger, and that's because as you go down, chlorine is a larger atom than fluorine, bromine's larger than chlorine, iodine, and you can see so the bond length increases. And then, but you guys will notice the dipole moment. Okay, that's kind of the, you see that is very tied to the electronegativity difference. Basically, you take the electronegativity of hydrogen, which I believe is 2.1, and you take the electronegativity of fluorine, which is 4.0. 4.0 minus 2.1 is 1.9. That has the greatest dipole moment. That means you're going to have the, because fluorine's going to pull on the valence electron of hydrogen much stronger than chlorine would. You can see as the electronegativity difference decreases, so does the dipole moment decreases. The greater the difference in electronegativity, the more polar is the bond. Okay, so they're trying to show this with color. The more red it is, the greater the electron density, and so electrons are very much the valence electrons are spending much more time around the fluorine nucleus than the hydrogen, as opposed to the iodine to the hydrogen. Lewis structures, okay, you guys, we're going to practice Lewis structures. I'm going to remind you guys. It says focus. Your math homework can wait. Major league pitchers hire people to do math for them. Hopefully you don't have a parent like that. Hopefully you have a parent that recognizes the importance of education. Okay, you know what? Before that, so you guys, let's do a practice one. Let's say we had to do the Lewis structure for cyanic acid. Okay, so I'm going to remind you guys we did this last year. So the first thing, if we want to draw the Lewis structure, we kind of want to show how the atoms are arranged, what kind of bonds are present. You first determine the number of valence electrons. So you count the number of valence electrons. We have hydrogen. Hydrogen, you guys should know, has one valence electron. We have carbon. And the valence electrons, carbon has a total of 6 electrons, but only 4 of them are the valence electrons. So there's 4 from carbon, 1 from hydrogen, that's 5. And then nitrogen is here. It has 5 valence electrons, and so that makes a total of 10. So I write down 10. The next thing you got to do is just arrange your atoms. You want to put the element that you expect to form the most bonds in the middle. Whenever you guys have carbon, always put carbon in the middle. Just the way it's written there does not necessarily mean that's how it's going to be in your Lewis structure, but in this case, I'm going to put carbon in the middle. So then where do I want to put other things? Then I would probably, you know, let's just say I put it like this. And you guys, sometimes with Lewis structures, you get it wrong. That's why I would encourage you guys to do it in pencil so you can erase it. So obviously, if these make up a compound, they're going to be held together. They're going to be sharing electrons. They're all nonmetals. So what I'm going to do is I'm going to make a bond right off the bat. A line indicates 2 electrons. Those are that's a shared pair of electrons. So then I count my electrons. I got 2 here, 2 here, that's 4. There's a total of 10. I still have 6 more electrons I got to find a home for. Now you're going to tend to write these as lone pairs. Lone pairs are valence electrons that are not being shared. So I'll just put 2, 4, 6. Okay, so let's say I do that. Let's say I'm feeling pretty good. The last thing you got to do is check the octet rule. You guys remember, the vast majority of elements, atoms, want 8 electrons in their outer shell. With the exception of hydrogen. You guys know hydrogen. You guys can see hydrogen just needs a total of 2 electrons to fill its outer shell. So hydrogen looks good here. Nitrogen, let's look at nitrogen. It has 2, 4, 6, 8 valence electrons. Nitrogen looks good. Let's look at carbon. 2, 4. Carbon only has 4. It hasn't satisfied the octet rule. That's a good indication that this is not the correct Lewis structure. So what you do with that is you take a lone pair and you make it a shared pair. So obviously these are my only lone pairs, so I'm going to take a lone pair. You know what? I'm going to make a shared pair. So rather than a single bond, I might anticipate, oh, maybe there's a double bond. That means that rather than sharing one pair of electrons, there's two pairs of electrons that are orbiting carbon and nitrogen. So look, nitrogen is still good, 2, 4, 6, 8. Now look at carbon, look, I'm almost there, 2, 4, 6. It's not quite there. That means, oh, it's still not right. Once again, what do? I take a lone pair, make it a shared pair. I'm going to take another lone pair, make it a shared pair. And in actuality, if you guys count it, the octet rule is satisfied for all of them with the exception of hydrogen, which has 2. This is the correct Lewis structure. Cyanic acid actually has a triple bond between the carbon and nitrogen. You guys, this is where the Lewis structure gives you a lot more information than just the formula. This is the formula. The Lewis, you wouldn't be able to tell that this had a triple bond until you did the Lewis structure. All right. Oh, and you guys can tell, and then with this, you can imagine this, if you had to say, what kind of molecule is this? Is this a non-polar or a polar? You guys shouldn't imagine that's a polar molecule. You guys, you have the more electronegative atom on this side, so there's going to be a lot greater electron density on this side of the molecule than that side of the molecule. Okay, we want to introduce this concept called resonance. So here's ozone. Ozone, this is an allotrope of oxygen. Remember, oxygen is normally O2, but sometimes you can get O3 ozone. That's their ozone layer that protects us from UV rays, right, in the atmosphere. So if you were to do the Lewis structure, just like we do here, you would come up with this. You'd have a single bond and a double bond. But in actuality, this is not what we observe when we do experimentation. You guys can imagine, if you're going to share a double bond, think about what's going to be different between a double bond and a single bond. When you guys agree, don't you expect a double bond to be stronger? Because rather than sharing one pair of electrons, it's sharing two pairs of electrons. And not only is it stronger, it's also, you can imagine, it's going to be shorter. If these are sharing two pairs of electrons, you can imagine when you expect the oxygen atoms to be drawn closer together because of the extra strong attraction, strength of the bond. So what you find is, in actuality though, you don't find one longer bond and a shorter double bond. What you actually find is, you find two bonds of the same length that are somewhere in between a single bond length, a longer single bond length, and a shorter double bond length. So what's happening is what we would call resonance. Resonance is kind of like, think about when you strum a guitar, right? You just strum it and then it just kind of reverberates. You might say the string is resonating. It's kind of going back and forth. It's kind of like that with the bonds. So what will actually happen is, see what we're showing here is, it'll actually have the bonds, it'll actually have two bonds of equal length, 1.278 angstroms, 10 to the negative 10 meters, indicating that those are the same size. So what's going to happen is, it's going to resonate between these two forms. So whenever you guys have a situation where you have a double bond and then a single bond, you have to contemplate the possibility that there was going to be resonance. So what's happening here is, what can happen here is, let's say a lone pair here will actually go here, you guys see, go here to form a double bond, and then what will happen here, now there's too much strength because there's too many valence electrons around the central atom, so then the shared pair of electrons here will be bumped here and become a lone pair of electrons orbiting just this oxygen, and so they'll kind of resonate back and forth. So when you see that, when you see a double bond adjacent to a single bond and you see lone pairs that can cause resonance, that's when you have to take into account there's probably going to be what's called so we'd say oxygen ozone has two resonance structures. Okay, and it's saying just like blue and yellow come together make green, these come together, these kind of exist, right? That, just imagine electrons are constantly going back and forth and it's resonating between these two structures. So here's another example of a resonance. Here we have HCO2. Once again, what do we see? When you have a double bond with a single bond and you have some lone pairs of electrons. So you just think, and you know what, when you guys create a Lewis structure, if you guys just look at your Lewis structure and you think, you know what, could that look differently? Really, is there any reason why there should be a double bond between this carbon and oxygen and not this carbon and oxygen? So in that case, you should think, when you write a Lewis structure, you have to consider, could there be a resonance structure? And if you could write it a different way, then most likely it's going to have a resonance structure. And so in this case, what do you see happens? A lone pair of electrons here can form the double bond. You guys see that? It's missing a lone pair. But then what does that do? Then if you had two double bonds here, then you have 10 valence electrons for the carbons, too much strain on the carbon. What's going to happen is the shared pair of electrons would then be bumped here as a lone pair, and this would resonate back and forth. We'd say, in this case, what we're saying is the electrons aren't localized, meaning there's not remember this is two shared pairs of electrons, those are not localized between just this carbon and oxygen. We'd say it's delocalized. that pair of electrons can be between that carbon and oxygen or between this carbon and oxygen. That's what delocalized means. Okay, last thing on resonance. This is a pretty common compound, benzene. A lot of organic compounds, a lot of the smells, a lot of flavors associated with fruits and things like that can tend to form these like benzene rings. And you can see what it is. It's a 6 carbon. You guys should remember this even from biology. You have glucose, which can form a 6 carbon ring, and then you have ribose, which can be a 5 carbon ring. But what you can see here is, so if you were to draw the Lewis structure for this, you'll notice carbon is satisfied. So if I gave you this formula, it's C6H6. The only way you're going to get a proper Lewis structure where the octet is satisfied for all is if you draw a benzene ring like this. And what you're going to have is alternating double and single bonds. Well, like we had said before, is there really any reason why there should just be 2 pairs of electrons shared between these carbons and not those carbons? If you think about it, isn't there another way you could write it? Can you put the double bond between those carbons and then put the double bond between those carbons? What we'd say is those are resonance structures, 2 resonance structures describing the benzene ring. And when you get into organic chemistry, if you go organic chemistry, they call it OChem in college, you can imagine this just gets kind of tiring because you deal with so many of these types of organic molecules that have a lot of carbons in it. It gets kind of tiring writing it. So what you do is you just write a ring, and it's just known that at the vertex of the where they join, those are carbons. And then you just recognize there has to be a hydrogens coming off, and you just don't show the hydrogens. This is just kind of an abbreviated way to write it. So this could be written like this could be written like this. So what do they end up writing it, the whole thing? They just put a circle here indicating that the alternating single and double bonds can resonate between the 2 structures. All right. You guys, there's a few exceptions to the octet rule. I think I brought this up last year as well. Ions are molecules with an odd number of, you can have actually odd number of electrons. You remember we've been talking about pairs, shared pairs, and lone pairs. Sometimes you can have odd number. It's not very common, but that does occur. And you can have a situation where you have less than the octet, and you can have a situation where you even have more. Like for example, here, if we were to do NO, right? Let's say I gave you the formula NO. You remember what you do? You count the number of valence electrons. Nitrogen has 5, oxygen has 6. That's 11. Obviously, that's an odd number. You're not going to have just shared pairs and lone pairs. So if you guys were to do the Lewis structure for this, you would come up with this or this. And you can see in both cases, there is an exception. You can see octet satisfied for oxygen, but here, 2, 4, 6, 7. And the same thing here, 2, 4, 6, 7 for the oxygen. That's what we call a radical. And you can imagine, because you don't see those very often, you might imagine, oh, those are probably unstable. And so those are free radicals. In fact, when you have this, you got to be careful with your exposure to free radicals, especially in some foods you eat. You can imagine that's a pretty unstable situation, and so you can imagine when that comes in contact with other substances, it's going to cause more potential for reaction and oftentimes not very beneficial. So those are called free radicals. So just remember, when you guys think odd number of electrons, think free radicals, think unstable, think pretty reactive. And you guys, here's a situation. We have BF3, boron trifluoride, BF3. And if you did it, if you actually count the number of valence electrons, you can come up with any of these scenarios. And you'll notice, but in all cases, here, this is the thing. I could see if you guys were to do BF3, count up the valence electrons, you would set it up, and to satisfy the octet, I could see you set this up. And you guys can imagine if you drew this, you're like, is there any reason why the double bond should be there? Can it be there? Can it be there? Right? These would be resonance structures associated with this Lewis structure. But in actuality, what they find experimentally, you don't have one shorter double bond and then 2 longer single bonds. What they find is they find 3 bonds of equal length. So what does that indicate? Not just resonance, but they actually find a bond length associated with a single bond. So you guys would look at this and you're like, well, wait a minute. Okay, let's say I count for all my electrons, but you guys will notice boron, 2, 4, 6, it only has 6. You're like, wait a minute, it doesn't satisfy the octet rule. Boron is a frequent exception to the octet rule. In fact, sometimes you guys will have that. These atoms in the second period here, they can tend to be satisfied less than an octet. And so it'll actually exist like that. So unfortunately, that's an exception that exists. You guys don't get mad at me. I didn't make it up. Talk to God about that. It just happens. Oh, look at this. You guys remember some atoms can actually exceed the octet. If we do count for all the valence electrons in PCl5, we would set this up. But obviously, clearly, you go, wait a minute, look at phosphorus, 2, 4, 6, 8, 10. We're saying phosphorus has 10 valence electrons that are orbiting its nucleus, and in fact, it actually does. So phosphorus can be an exception. A lot of times, phosphorus can have an excess number of valence electrons. And a lot of times, the reason for that is, they think about, especially in this third period here, you guys remember this is the third energy level, and remember the d orbitals? So it has empty d orbitals. So the theory is that the extra electrons are going to occupy an empty d orbitals in that third energy level, and that can help explain why those can actually have more than an octet number of electrons. So presumably d orbitals in these atoms participate in bonding. The strength of a bond, almost done here guys, the strength of a bond is measured by determining how much energy is required to break the bond. We call that bond energy. So if we had this Cl2, the amount of energy needed to break that bond, so we have two separate chlorine atoms, that's called the bond energy. Or the bond enthalpy. More specifically, it's called the bond enthalpy. A lot of times we call it bond energy. The bond enthalpy for a CCl bond is 242 kilojoules per mole. That means for every mole of Cl2 molecules I have, it would take 242 kilojoules to fully separate all of those chlorine atoms. So, guys, just looking at a table, I don't know if you guys can see this. So there's certain bond enthalpies. So a carbon-hydrogen bond would have a bond enthalpy of 413. It's relatively high. A carbon-carbon bond is 348. So that means that the bond, the attraction between the carbon and the hydrogen is much greater. The bond is much stronger between the carbon and hydrogen because it requires more energy to separate it does than the carbon-carbon bond. So bond enthalpies are positive, and why is that, guys? Because it requires energy to break those bonds. And therefore, it's an endothermic process, right? So these are all positive values. When we say bond enthalpies, they're all positive values. I'm going to show you guys how you can use these bond enthalpies to ultimately calculate an enthalpy of a reaction. We'll show you what we mean by that. But check this out, guys, and you'll notice, look at here. The single bonds here, they range from like between 200 and 400. Now look at the double bonds. This is up around 600, 800. Because what do we say about the double bonds, triple bonds? They're sharing 2 or 3 pairs of electrons. Therefore, it's going to be a stronger attraction as more electrons are being shared. Therefore, it's going to require more energy to separate those. So we can do a bond enthalpy. So for example, here, check this out. Let's say we have this reaction. You guys write this down on your notes. We have methane reacts with chlorine to form methyl chloride. And you guys see what's happening? Essentially, one of the chlorines combines with one of the hydrogens, and then the chlorine attaches to the methane molecule. Here's how you can calculate the delta H. You can write this down. You can take the sum of the bond enthalpies of the bonds broken minus the sum of the bond enthalpies of the bonds formed. Okay? So, here's what we can do. I'm going to go back to this. What I can do is just kind of account for all of the bonds that are broken and all the bonds that are formed. So here's probably the easiest way to do it. I wouldn't even use that formula because that gets kind of confusing. I would go to my table of bond enthalpies. So first of all, what I would do is I'd break apart all of my atoms. So you guys can see here, right? Just so you guys can see what's going on. This would be, just so you can see. And this is where it helps to draw Lewis structures so you can kind of see what's going on, right? So I got that, and then it's going to form. And then, so what I could first do is just show all of my bonds breaking. Look, I have a carbon-hydrogen bond, and how many of those do I have? I have 4. Carbon-hydrogen bond is 413, so I go 4 times 413, okay? And that's going to be 52, okay? So it's going to require that much energy to break up all of my carbon-hydrogen, and then I need to break up a chlorine-chlorine bond. I look at chlorine-chlorine, that is located right here, 242, and there's only one of those, so that's 242. So how much total energy do I need to separate all the atoms of my reactants when I just add these together? And you know what I'm going to put? I'm going to put a positive. Why do I put a positive? Because it requires energy to break those bonds. Then what happens? Just imagine all the atoms the bonds are broken. Then imagine we're forming the bonds here in the products. So what bonds am I forming? I'm forming a carbon-hydrogen bond. And how many of those? 3 of those. So I go 3 times 413, right? But I'm also forming what? A carbon, that's how much? That's 1239. But I'm also forming a carbon-chlorine bond. carbon-chlorine bond is 328. And you notice there's just one of those, so I go 328. And notice I'm adding these together, right? And then, what else am I forming? I'm forming a hydrogen-chlorine bond here. Hydrogen-chlorine is right here, 431. So I add those up, 6, 9, 7, 9. Now, but you guys, what kind of sign would I give it? Remember, these are bond formation. So remember, it takes energy is required to break bonds, and energy is given off in the formation of bonds. So in the formation of these bonds, this is how much energy is given off. That's a negative sign. So then, what do you guys think I just do with these? Well, this is how much energy was required to break the bonds between all the atoms. This is how much energy was given off in the formation of the bonds between all those atoms. What do? You just add those together. I think that's essentially what that previous equation was telling you to do. So I go 4, 0, 1. You guys can see, and basically what do we notice? More energy was given off in the formation of these bonds than was required in the breaking the bonds, and overall, so what happens? Overall, my answer is negative 104. That's kilojoules, and then the units would typically be kilojoules. Actually, it's kilojoules per that reaction. So for every 1 mole of that reacts with 1 mole of that to produce 1 of that and 1 of that. And you guys can see what type of reaction overall was it? It's an exothermic reaction because more energy was given off in the formation of bonds than was required in the breaking of bonds. So you can see this is another way that we can calculate. Remember our previous unit in thermochemistry was the delta H? This is another way we can calculate delta H by using a table of bond enthalpies. Once again, just adding up all the bonds that are broken and all the bonds that are formed, remembering that to break bonds is an endothermic process, positive enthalpy, and the formation of bonds is an exothermic process, and therefore a negative, and then you compare the two, and that's what we get. And that's kind of what they're showing here. They're starting with what we're starting with here. Then you guys see we're going to a higher energy state because it required energy to break some of those bonds, and then when they formed, there was more energy given off in the formation of the bonds than was required in the breaking of bonds. And so overall, what do we find? I assume I did my math right. We'll see. So essentially, that's essentially what they're doing here, and we get negative 104 kilojoules. Okay, now I promise we're almost done. I only have like a minute anyways before I got my next class. So you look here, notice there's a correlation. There's a single bond between carbon, double bond between carbon, a triple bond between carbon. What do you notice? The bond length decreases from a single to a double to a triple, and that shouldn't be surprising as they're sharing more electrons. That's pulling the nuclei closer together. The bond length is shorter, and therefore it shouldn't be surprising that the bond energy or bond enthalpy is going to be greater for a triple bond than a double bond than a single bond, because as those are closer together, it's going to require more energy to separate those. And